All right, well, we'll get started here. So today I'm talking about quadratic equations and, oh, there it is. It's like, where's my bag of markers? How to solve them. So I'll just start with a couple of examples to illustrate the different things that are going on here. And once we've got a few examples under our belt, I'll try to write out the general result. All right. So I'll just tell you at the start, though. So what is a quadratic equation? It's something of the form ax squared plus bx plus c equals to 0, right? With a, b, c real numbers, and a not equal to 0, right? This is a quadratic equation, and this marker is worthless. Yeah. Ideally, it would be in the trash can, but the more important point is it's far away from me, so I can't use it on the board again. So, example 1. Suppose we're solving x squared plus 6x plus 5 equals to 0, right? So the first method that we could use, I would say, is just factoring, right? So if you can just straight up factor it, then great. This is x plus 1 times x plus 5, right? So we can factor this one, right? So then what are the solutions? Exactly. So the solution is x equals to -1 and x equals to -5. So here you go. The solutions are, there's two solutions. They're distinct. They're real. There they are. Let's take a minute to do a little bit more. Let's graph. Let's go ahead and graph the polynomial. What I mean by that is let's look at the picture that corresponds to this, right? So we're going to try to graph y equals to x squared plus 6x plus 5, right? Now, there's three really easy things to pick off for this graph, right? On the algebra we have on the board. What does it mean when we solve this equation? You've got x plus 1 times x plus 5 equal to 0. What does that mean graphically? It means that y is equal to what at the solutions? 0. Right. So we know 2 points on the graph. In particular, -5, right? And -1, right? Those are 2 points on the graph. What's the third point on the graph that we can get? It's pretty easy to get. So we get x-intercepts from putting y equal to 0. We get y-intercepts from putting x equal to 0. What happens when you put x equals to 0? Yeah, right. So if we put x equal to 0, gives y equals to 5. That's our y-intercept, right? There's just one y-intercept. There can't be two for a function. So it's about the same. If I was doing my graph right, it should be about the same distance from the origin, right? It should be the same distance from the origin as the x one here. So it should be like up here somewhere. And every time, guys, every time one of these things, it's the graph. Oh, poor choice of, man. I always choose the wrong scale on these things. One of my many failings. Anyway, there's a couple things you can use to aid your graphing. So the vertex, the place where the parabola turns around, it's always halfway between the roots. Roots is another word for zeros. All right, so you could say the roots of the polynomial are -1 and -5. All right, roots, zeros, these are synonymous. And So halfway between minus 5, there's this what's called axis of symmetry, right? It's right there. And so the vertex is where it turns around. I'm not going to try to do that precisely. I'm just going to kind of just say, okay, so basically this is a sketch of the graph, right? So roughly speaking, that is the graph in blue of the parabola. Sorry, my parabola sketching up at that level of the board's not great. But anyway, it's basically that. So it's always like, parabolas are always basically like this, right? Or they're like this, right? It's either like opens up, it opens down. Can you guys tell me? When's it going to open up? When A is positive. It's going to open down when A is negative, right? Okay. So that's example 1. The solving is this part, right? The graphing is that part. Let me flip the script here for a second. Imagine I first gave you the graph. Could you tell me the solutions to the corresponding equation? I mean, it's pretty easy, right? You just look for, are there any x-intercepts? That's where the solutions would be, right? If you were given the graph, you could solve the equation. We don't usually present the problem like that because it's a pain, but in principle, it could be, right? If you're given the graph for a polynomial, you could read the solutions from where the x-intercept crosses, wherever the x-intercepts are found. Example 2. Let's see here. Example 2, we could have something like x squared plus 18x plus 57 equal to 0. All right? Oh, that's still, I didn't want 57. I wanted 157. My bad. There, better. Can you factor this? I can't factor this. All right, so what I'm going to do is I'm going to complete the square. So factoring looks bad. Go to complete the square mode. All right, so we do x plus what? Quantity squared. We do what? We take half of the coefficient of x, since we have a equals to 1 in this problem, right? If there was if a was not equal to 1, we have to factor it out, all right? I'll do one of those maybe next. So this is x plus 9 quantity squared. And if I put that, I have to do what? I have to subtract 9 squared, which is what? It's 81, right? Minus 81 plus 157. What's 81? Take away 81 from 157, what do you get? So you've got, what is it? X plus 9 squared plus 76 equals to 0, right? Now, there are different ways to go here, but let me show you a nice way to think about it, all right? So we've been emphasizing factoring a lot, right? But the other way we could go is taking the square root of a square, all right? If we take the square root of an equation, we have to be careful. We have to allow for plus and minus. Let me kind of show you that. So just sidebar here, something simpler. If I had x squared equals to 4, right? And I take the square root of both sides, what do I get? It would seem to indicate what? X equals to what? 2, right? But it's inaccurate. And the reason for that is the square root of x squared is not just x, actually. The square root of x squared is the absolute value of x. It's actually the absolute value of x, right? Check it out. So like the square root of minus 2 squared, what is it? It's the square root of 4, right, which is 2. What's the square root of 2 squared? It's the square root of 4, which is 2, right? So you know that the absolute value of minus 2 is equal to the absolute value of 2 is equal to 2. This square root of x squared is a formula for the absolute value of x. It's always positive, right? The square kills the negative if it's there, and you get back the magnitude of whatever you're feeding to it. It's the absolute value function. So what I'm trying to say here is that the solution's not just 2, it's actually plus or minus 2, right? So you don't want to go through this every time you do this, right? So what you do instead is you have a theorem, and the little theorem is this, all right? If we have A equals to B, and they're both positive, right? Or 0, then the square root of A is equal to plus or minus the square root of B. That's still not what I want to say. I wanted to have A squared equal to B squared. Well, anyway. I mean, it's not wrong. It's just, let me just do it over here. So here for the example, we have x plus 9 squared equals to minus 76, right? So we can take the square root of both sides. When we do that, what I'm trying to tell you, I'm not getting to my point very quickly, is you got to put plus or minus, because there's two possibilities. Because that's actually an absolute value when you take the square root. But this time we've got the square root of minus 76. What is that? Well, let me write it this way. That's plus or minus the square root of minus 1 times the square root of 76, right? In other words, it's plus or minus I times the square root of 76. See, because the square root of minus 1 squared is minus 1, right? I is another notation, actually, for the square root of minus 1. This notation was introduced by Euler in like the 18th century, for what it's worth. But so what does that say? The solution is what? X equals to minus 9 plus or minus I times the square root of 76. So if we allowed for complex solutions, there they go. That's what they are. All right? So we can complete the square, and then here's the new thing I'm saying. Isolate the square, and then they take the square root of both sides. That gives you the solution. What's the graph look like in this case? Well, what's a method for graphing that we can use? Always. Well, I look at this formula, right? Something special happens at minus 9, right? See that? At minus 9, the squared term is 0. So maybe I should look around minus 9. Maybe that's interesting, right? So I'll start at minus 7, minus, oh, excuse me, what's too smaller than minus 9 is not minus 7. What is it? I should do minus 10, right? Minus 11. And then maybe minus 8 and minus 7. Here's my x values. And let's put my y values over here, where y is equal to, you know, x squared plus 18x. Well, let me write it this way. Y is equal to x plus 9 squared plus 76, right? So if we're going to graph, we can make this table of values, and that's a way we can make the graph, right? You connect the dots, basically. I had 3 dots for the last one. They were easy to find, right? Here, it's not quite so easy because there aren't any x-intercepts, right? This says no x-intercepts. It says there's no place where a real number gives you 0, because it happens at complex numbers. Now, at 9, at minus 9 rather, it's pretty easy. What do you guys tell me what the output is? You look at this formula. What happens when you put minus 9? Plug in minus 9, you get 0 squared plus 76, right? So the output 76 at minus 9. What happens when you put in minus 10? When you put in minus 10, you get 1. You get minus 1 here plus 76. So you get 77 at minus 10. And the same thing happens at minus 8. At minus 8, you get minus 8 plus 9, which is 1. 1 squared plus 76 is 77. What happens when we plug in minus 11? Well, we get minus 11 plus 9, which is minus 2. Minus 2 squared, well, that's 4, right? So we get 4 plus 76. We get 80. And the same thing happens at minus 7. So that kind of tells you what's going on here. I will not be drawing, I'll try, I don't think I'll be successful in drawing this to scale, but I'll make a sort of a heuristic picture here. Minus 9, and then up here, a ways. I won't do the same scale on the y and the x-axis, okay? So its vertex is at 76, that's where it turns around, and then it kind of opens up from there, right? And so the way I've drawn this, it's going to open up really like shallowly. Something like this. Now so if you have, relative to your scale, it's opening really shallow, the parabola looks more like this. Can you tell me oh, I haven't done a very good job, have I? What's the y-intercept? This is inexcusable, we can do better. What's the y-intercept? Don't draw it like I draw it just yet. What's the y-intercept? You guys tell me. You can at least do that, right? The y-intercept here is the constant term, right? That's what happens when you put x equal to 0. So the y-intercept for this one is 157, right? So 157, well, that's like double this, isn't it? It's like up here. So my picture really should look more like this, yeah? So if I ask you to graph a parabola on your test, what's going to happen is I'm going to have some graph paper there, all right? Printed on the test so that you can do it there carefully, and I'll probably define the scale on the graph so there's no ambiguity, you know? You won't be faced with the daunting task of freehanding graphs on top of white paper, you know? I mean, you can do it. I sometimes will ask for a sketch of a graph without a graph. But if I ask for a sketch, I'm not being as critical of like specific points being in the right place, you know? This is the difference between sketching a graph and graphing carefully. I'm sketching because I can't graph carefully. I don't have graph paper on the board, you know? Any questions? So what are the solutions in example 2? Well, I boxed them in, right? They're complex solutions. And if the solutions are complex, we say no real solutions, right? No real solutions here. No real solutions. And what do we get to say graphically? No what? No x-intercepts, right? Let me do another example, example 3. This one I'll make a little bit uglier. Suppose we have 2x squared plus 4x plus, I don't know, let's say 6. Now you could try to do the, you know, the factoring with the numbers, but what I'm going to do, because I think we need to see more of it, is complete the square. All right, so completing the square here looks a little different. Completing the square here, I want to factor 2 out, right, to start with. And admittedly, after I factor that 2 out, I feel kind of silly to complete the square. Maybe I don't. Well, oh, for a second there, I thought it factored because, you know, the 3, maybe 1, like I could do like 3 minus 1, which would give me 2. But the trouble is what? I don't have the right signs for the factoring to happen, right? If I had like a minus 3 here, I wouldn't use completing the square. I would just factor. But we don't, right? So let's complete the square. So we have 2, and then we do x plus 1 squared. And then I have to subtract 1 squared, which is 1. All that happens inside the parentheses, which I'll make red here. Right? So what do we have? Notice that you can just divide by 2, right? You're solving an equation. You've got a number that's factored out front. What do? Divide both sides of the equation by 2. Get rid of the 2, right? I can divide this by 2. I divide that by 2. What's 0 over 2? 0 over 2, still 0, right? So what I have here is I have x plus 1 squared plus 2 equal to 0, right? And so what does this give me? This gives me x plus 1 squared equals to minus 2. Now I can take the square root of both sides, remember, plus or minus, to cover all the possibilities. So this gives me x plus 1 equals to plus or minus the square root of minus 2. But that's equal to plus or minus the square root of minus 1 times the square root of 2, which is plus or minus I root 2. So what are my solutions? I just have to solve for x, right? And solving for x gives me x equals to minus 1 plus or minus I root 2. So again, this time the solution was complex. If I was to graph this, no x-intercepts, right? We do another one that's kind of like this. Example 4. Let's say 3x squared plus 12x plus 15 equals to 0. Let's see if we can solve this one. I'm being kind in the sense that I'm making sure we don't end up with fractions in the calculation, yeah? At least for now. So what would you do? First thing to do, this problem. You guys tell me. I got to do all the work in here? You guys are worn out from the game this weekend? Was it? I believe I heard a 3 parentheses. Right, so first thing we can do is divide the equation by 3, get rid of it, right? We don't need to keep that 3. Throw it out. Divide both sides by 3. What's the difference? Why couldn't we throw the 3 out in our previous work? Well, our previous work was about factoring an expression. And you can't just divide an expression by a number willy-nilly, like that changes the expression. So if you're just trying to modify the format of expression to factor it, you can't just throw away 3's, you know? But this is an equation. So we can divide an equation by a non-zero number. That does not change the solution set, and therefore it's the same quote-unquote equation. Anyway, here we go. X squared plus 4x plus 5. Complete the square. We've got x plus 2, quantity squared, minus 4 plus 5 equals to 0. Oh, shnikes. I think this is another example of the same kind. So we have here x plus 2 squared equals to what? X plus 2 squared looks like equals to minus 1, yeah? You put the 1 on the other side, becomes minus 1. How do we solve it? We take the square root, allow for the plus or minus. What does that look like? X plus 2 is plus or minus the square root of minus 1. But remember, square root of minus 1 is what we call I. Right? That's our notation for it. Mostly because the square root of minus 1 is hideous. Nobody wants to write that. Right? And so move the minus 2, to subtract 2 from both sides, and we have the solution. X equals to minus 2 plus or minus I. All right. I feel like I'm a broken record. I keep giving you another example with a complex case, but I think this is important because we haven't dealt with many of these yet, right? let's see here if I can come up with an interesting one. How about 13x squared plus 26x plus 2 equals to 0. Let's see if we can solve this one. So you guys tell me, what should I? Oh, my bad. I was supposed to put the last term as 13, 2. I mean, we can keep it 2. Do you guys want to keep it 2? No? Okay, we'll put it back to 13 then. We'll put it to 13. It might be helpful for you guys to see it with 2. That'll make it uglier, like a lot uglier. Okay, there it is. So first thing, I think you guys know, we're going to factor out 13, right? And so we get x squared plus what? 2x plus 1 equal to 0. Divide the equation by 13. I get x squared plus 2x plus 1 equals to 0, right? And you guys tell me what to do with that. This is one of those places where some of you would say factor it. Others of you might say complete the square. But we should all agree we get what? X plus 1 squared minus 1 plus 1 if you complete the square, right? So it's x plus 1 squared equal to 0. However you choose to do the algebra, we should get to x plus 1 squared, right? So this is the other case, right? There are really 3 cases with the quadratic formula. You can either have distinct real roots, like in our example 1. You can have complex roots, which always come in a conjugate pair. Notice it's always plus or minus the same multiple of I. Those are conjugate pairs. And the other possibility, of course, is we get the same solution twice, right? This gives us x plus 1 equals to 0. So that tells me that x equals to minus 1. So we like to think of this as being the same solution minus 1 repeated, just to sort of keep the story the same, right? There are always 2 solutions. It's just sometimes the 2 solutions are complex. They come in a conjugate pair. Sometimes they're distinct and real, like this one, example 1. And sometimes they're the same solution twice. So there's always 2 solutions if we count, multiplicity. Let's see here. So minus 1 is the x-intercept, right? And what's the y-intercept? I don't know if I've given myself enough room, but let me make that minus 1 a little bit closer. I'll try to keep the same scale here. So the y-intercept, if I'm graphing this one, right? If I'm graphing y equals to 13x squared plus 26x plus 13, well, the y-intercept is what? (13), right? Because we put x equal to 0, so the constant term is the y-intercept. Do you see it? So, I mean, roughly speaking, if this is 1, so I got like 1, 2, 3. Well, anyway, it's up here somewhere. That's probably not far enough either, but roughly speaking, it's like that. Where's the vertex? Where's the vertex for this parabola? It's at -1. So the vertex is where the x-intercept is. That's what happens in this case, right? I like to say it bounces. So it kind of bounces off the graph. We bounce that. So there it is. And so this is 13 up here, right? So if I ask you to, label interesting features of the graph, well, what are interesting features of the graph? Y-intercepts, x-intercepts, the vertex. These are the interesting features, right? Any questions? Okay, so there is a another way to look at these. See here. Let me do another kind of relatively easy example here as a backdrop for what I'm about to do. So let's look at y equals, well, not y, but excuse me, x, let's say plus 3 times x minus 3 equal to 0. You're like, well, that was really easy because why? My littlest brother, when he was little, he used to say, "'Cause be why." So that was his argument. "'Cause be why." Sort of an argument. But so here, we either have solutions x equals to minus 3 or x equals to 3, right? And so we can graph. And so we get minus 3 and 3, roughly speaking. And so I'm graphing y equals to x plus 3 times x minus 3. What's the y-intercept in this case? What did you say? You said what, -9? Right? So we could do this, right? We could say this is x squared plus 3x minus 3x minus 9, right? So really, this is x squared minus 9 if we want to go back to standard form. If you did that, then you can read it, you can look at it and go, aha, the constant term is minus 9, that's the y-intercept, right? If you write it in standard form, the y-intercept is the constant. So there it is, minus 9. And once you know those 3 points, you can graph the parabola, right? More or less. Where's the vertex? Oh, man. Can't graph. The vertex in this case is where? It's actually at the what? The vertex is the place where the parabola turns around. Here the vertex was at -1 in example 5. So the turning point, it's right there, right? Vertex and y-intercept, one and the same. Same point, right? What is that point? That point is 0 minus 9, right? That's the coordinates of the vertex. If I ask the question, where is the vertex at? What I'm asking for you to tell me is the coordinates of the vertex, right? Now, if you tell me the vertex is at x equals to 0, I'm probably going to give you full credit, right? But, you know, the best answer is the coordinates because that completely describes where it is, both x and y. All right, so the time has come for a certain derivation that we must do in here. I've kind of done half of it before, but we're going to go through it again here. So I'd just like to summarize methods of solution. What are the methods of solution we've seen today? There is factoring, right? So factoring is when ax squared plus bx plus c, we work it out, it's a times x minus r1 times x minus r2, right? Let me just stop here and take a minute to derive something. Notice that this is, we can work it out, this is ax squared plus a times, well, minus a times r1 plus r2 times x, and then plus r1, r2, right? So if you look at this, we see that there are actually some easy formulas that relate the coefficients of the parabola to the roots, right? And what are those formulas? Well, let me show you. So this b, right, it has to match what goes over here. So we get b, or, well, let me write it this way. We get r1 plus r2, oh, fine, in between step. B is equal to minus a times r1 plus r2. I think a more interesting way to write that formula is that the sum of the roots, r1 plus r2, is equal to what? Minus b over a. So this is a useful thing to know about. So the sum of the places where it's 0, it's just the ratio of minus b over a. I think it's interesting that c doesn't appear in this formula, right? And how about r1 times r2? What's that equal to? Well, we got what? We got c is this over here, right? So c is equal to r1 times r2, the constant term. And oh, I've forgotten something. You guys tell me where I'm wrong. My bad. A most grievous mistake I have made. I have failed to distribute. I failed to distribute the a. So we get a times x times x. We have the middle term that has a, but this last term also should have an a right here. Right? There should be an a there. So we generally have c is a times r1, r2. So do these formulas check in our example? What's the roots? In this problem, we have r1 is minus 3, and r2 is equal to 3. You could label them whichever way you wanted to, but there it is, right? What is the sum of 3 and minus 3? Well, it's 0, right? Is 0 equal to minus b over a? Well, what's b in this problem? This says a equals 1, b equals 0, c equals minus 9, right? So notice that the first boxed formula is legit, right? The sum of the roots is 0. That is, in fact, also the value of minus b over 2a. And the second formula, a times r1 times r2, well, 1 times minus 3 times 3 is minus 9, and that is indeed the constant, right? So these formulas can be useful. The other method is completing the square. All right, so let's go through that. And we're going to go through it for an abstract, well, I say abstract, but I mean an arbitrary quadratic. So here we go, ax squared plus bx plus c. We do kind of we started this calculation the other day. So we do a times x squared plus b over ax plus c over a. Then I complete the square, so I've got like a, I do x plus half of that term. So that's b over 2a, quantity squared. I'm completing the square. To be fair, I have to subtract minus b squared over 4a squared, right? Because that's the square of this. And I still have the plus c over a, right? So, all right. So this then, I guess for, let me stick with it here. So this is a times x plus b over 2a squared minus, well, b squared minus 4ac over 4a squared. But I'm going to write that as 2a squared. Oh, fine, I won't. One more step, 4a squared. So that's a times x plus b over 2a squared minus the square root of b squared minus 4ac divided by 2a, all of that squared, right? So then what? What are we looking at? Well, we're looking at the difference of squares, right? we're looking at the difference of squares. So we can factor that as a times x plus b over 2a plus the square root of b squared minus 4ac over 2a. Or we can we get x minus, or excuse me, x plus b over 2a minus the square root of b squared minus 4ac over 2a. I'm using the difference of squares factoring, because upstairs I have a difference of two squares, right? So I do a plus b, big A plus b, a big A minus b. Here big A is x plus b over 2a. The big B is this mess with the square root divided by 2a squared. Aha, well now we have it factored, right? So what are the solutions? So I set this equal to 0, so we have solutions. X equals to, well, minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? See, because I can have a common denominator of 2a, so I can bring those two terms together, right? And I get the plus for the one and the minus for the other. There you go. This is what? This thing I just wrote. This is the quadratic formula. We could derive the quadratic formula from completing the square. Now, is this how I did the examples today? Did I find the solutions like this? This is not how I actually did the examples today at all, is it? Did I actually use the quadratic formula ever in here? No, because it's not really a good way. Because this formula, I just tell you, as a matter of practice, like, you will mess up using this formula. You're much more likely to be successful actually going through the mechanics of completing the square. It's not bad for given examples. So what we've actually done in here, in the examples today, instead of taking the path I did here to find the quadratic formula, we did what? We went basically from here to what? We went from here, we basically divided by a, right? Got rid of the a, right? We divided by 3 in the one example. We divided by 2 in the other example, right? And that brought us to x plus b over 2a squared equals to b squared minus 4ac divided by, well, 2a squared, basically. And then that gives us x plus b over 2a equals to plus or minus the square root of b squared minus 4ac over 2a. So that's this, what I'm writing over here, is the mechanics we did today in the examples. That's actually the path we followed in the examples for class. Like, that's the method. Isolate the square and take the square root above for plus minus, right? All right, so there's more to glean from this calculation, all right? There's more to glean. So let me show you here. This guy, we'll pick up right here. We'll pick up right here, all right? So if we write y equal to ax squared plus bx plus c, by the algebra on the other board, right? By the algebra on the other board, we can rewrite that as a times big parentheses. Well, excuse me, what I'm going to do is I'm going to, for the sake of not writing too much, I'm going to multiply the a through here and just write it that way. So I have a times x plus b over 2a squared, right? So I'm multiplying a through here to get over there. What happens when I multiply a through these two terms? What do I get? I'll write it out. So I get plus a times, well, minus b squared over 4a squared, right? Plus c over a. So let's simplify that. We can do a little bit better. We have a times x plus b over 2a squared plus what? Well, I'm going to do the c term first because it's nice, because it simplifies to just c, right? And then the a cancels with the a squared, and I'm left with minus b squared over 4a, right? All right, so we should like to think of this as like a function, right? A function is a thing that you put a number into and you get another number out of, right? I mean, I guess we haven't talked about that in here yet, have we? Did we? Wait a minute. Didn't you guys talk about domain? And yeah, so we talked about it. Sorry, don't let me take away what you've already done in here. So let's suppose this is equal to f of x. Let's call this whole thing f of x. This would make it a quadratic function. All right, a quadratic function is a function whose formula is a quadratic polynomial. And so you tell me, if we look at y equals f of x, when is this expression like biggest or smallest? Like, look at it. Like, whenever this square is 0, right, that's the smallest it can get. I mean, it's in magnitude, but then the question is whether a is positive or negative, right? If a is positive, then as x gets further and further away from minus b over 2a, this term gets bigger and bigger, right? That's the case of a polynomial, the quadratic opening upward, right? So when it opens upward, when a is positive, the minimum value happens, let me just write it down here rather than talking, a greater than 0 implies x equals to minus b over 2a gives max, right? Y equals f of x. And if a is less than 0, then x equals to minus b over 2a gives min for the graph. Right? The maximum, if it opens up, excuse me. Oh, I just did those exactly backwards. My bad. I think I said it right, but I wrote it wrong. I'm being optimistic here. As I said before, when it's positive, the minimum is the vertex, right? When it's negative, when a is negative, the vertex happens to be where the graph is maximal, right? So hey, notice that the vertex is where? It's at minus b over 2a, comma what? What happens when you put x equals to minus b over 2a? Well, it's really easy to see in the formula we just wrote down. See this? What happens when you put x equals to minus b over 2a? What are you left with? You're left with this right here, right? So this is, you get c minus b squared over 4a. So there you go. This is a formula for where the vertex is at. That's a formula for where the vertex is at. Now, a lot of times people like to use the language. They say the vertex is at h comma k. And if you use that language, notice that the graph of the parabola looks like this: a times x minus h squared plus k. So this is sometimes called the vertex form. Vertex form of quadratic equation. You see why it's a vertex form? It's the vertex form because if you have the quadratic equation in this form, you can read where the vertex is just directly. Right? Now, okay, so I've shown you these formulas, right? And there's a temptation to just write the formulas on a sheet and use them. And I would encourage you to do that as a double check to your work. But I think what's wise in terms of how to actually work problems is to go through actually these calculations I've shown you for an arbitrary one for the specific examples. Like, that's how to achieve the best success, is to follow these methods of calculation for specific examples, rather than just relying on the formulas blindly, all right? One other theoretical result I should show you. What happens if we take x plus and add it to x minus? What happens when you look at the sum of the roots? So I'm calling this plus and minus. We've also called it AKA root 1 plus root 2, right? Sometimes I call them R1 and R2. I sometimes call them x plus and minus just to, reflect the quadratic formula. But I mean, let's go ahead and do it. What do we got? We got minus b over 2a, right? let's say minus the square root of b squared minus 4ac over 2a, right? That's R1. And what's R2? Well, minus b over 2a plus the square root of b squared minus 4ac over 2a. So what happens? The terms that have the square root of b squared minus 4a, they're what? They cancel. And we're just left with minus b over a, right? So therefore, R1 plus sorry, there's something. Yeah, I mean, it's not wrong what I'm writing. It's just there was something else I was trying to say here. Oh, duh. Well, it's kind of silly. What happens if you divide this? What happens if you divide this formula by 2? R1 plus R2 over 2 equals to minus b over 2a. What's the significance of minus b over 2a, though? What is that? It's where the vertex is, right? This is the x value of vertex, right? So what does this tell us? This tells us that the vertex is always halfway between the roots. Add one root plus the other, divide by 2. This gives you the midpoint of the roots, right? All right, so a few more examples here. Example 7. Suppose somebody tells you y is equal to 13 times x plus 4 squared minus 19. All right? First question, where's the vertex? So I'm just asking you to match the pattern, right? Match this pattern to this pattern. What's h equal to? So 4, almost right, but we need, the vertex is where that squared term goes to 0, right? So we need minus 4. Notice it's a minus h in the formula. This is just like the issue with the roots versus the factors. And then what happens when you plug in minus 4? You get minus 19, so that's where it is. Right? Now my question is, can you solve? 13 times x plus 4 squared minus 19 equal to 0. Here's how I'd solve it. I would isolate the square. I've already got a square, right? That's lovely. So we have x plus 4 squared equals to what? Equals to 19 divided by 13. So I've got a square equals to a number. Now I take the square root of both sides, use my square root theorem that I have to put plus minus. Right? That theorem is ultimately really justified by factoring, but you know, this is a result we can use. Right? Take the square root of both sides. Remember plus minus because we're taking square root of square. And now solve for x. We got what? X equal to minus 4 plus or minus the square root of 19 over 13. So there it is. What's the y-intercept of this parabola? If I was to ask you that, what would it be? what do we do to find the y-intercept? We put x equal to 0, right? So you got two options. The one thing you could do would be to multiply this thing out and put it into standard form. Then you can just see that the y-intercept is the constant term, right? That seems like a pain though, doesn't it? Isn't it easier to just put x equal to 0? So we've got 13 times 0 plus 4 squared, right? Minus 19. So that's kind of big. 13 times 16 minus 19. What's 13 times 16? Well, it's 160 plus 48, right? So it's 208. 208 minus 19 is 198 less 9. 187? This problem's murderous. Is that right? Or have I just miscalculated? Somebody confirm or deny scene of the crime here. My calculator's back in my office. So far from here. Am I right? About the 187? 189? Oh, that's not nearly as interesting. All my murder jokes are gone. Oh well. Thank you. Something I haven't quite said today yet. The discriminant, we talked about that last time, right? Remember the discriminant? What's the discriminant? It doesn't hurt repeating this. Discriminant was b squared minus 4ac, right? And if you look at what we've done today, you can see why the case b squared minus 4ac greater than 0 gives you x equals to minus b plus or minus the square root of b squared minus 4ac over 2a, right? Distinct real solutions, right? If, on the other hand, the discriminant's 0, what happens? You just get x equals to minus b over 2a repeated, right? You get the double solution. The square root term drops out happily in the repeated root case. And what's the other case? The discriminant's negative. We get x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, right? But notice that in this case, we could rewrite this as minus b plus or minus I times the square root of 4ac minus b squared over 2a, right? In other words, this is a complex conjugate pair. Listen, I do want to take about 20 minutes in here to just do complex number calculations with you guys, just to try to get more comfortable about what that is and how it looks like. That's kind of an important skill for us to revisit. You probably saw it in high school, but just in case you didn't, like, we should go over that more, you know. I think there are some problems in Chapter 7 just about that. We're in Chapter 7 now, by the way. Should mention that at some point. My bad. But anyway, you can always kind of know where you're going by calculating the discriminant, right? In practice, I don't tend to do this. Like, I just either factor or I complete the square because it's just simpler than trying to remember all these formulas and apply them. But I should show you these formulas, you know. These are things you should be aware of, so I have. Example 8. Let's see here. Suppose we've got x squared minus 13x plus, let's say, 40 equals to 0. How should we solve this problem? So let me go back to day 1. Let's look at the factors. Well, look at that. 40 is what? It's 5 times 8, right? But it's also minus 5 times minus 8. I mean, it's various other things too. But once I see 5